Hello everybody, I'm Adam. In this problem, for the two planes given by equations x minus 3y plus 4z equal to 10 and x minus 3y plus 4z equal to 6, we're going to be doing two things. One, we're going to verify that the planes are parallel, and two, we're going to find the distance between the two planes. So for our first part, verifying that the two planes are parallel, first let's get a visual of what we're dealing with. So if we have two planes in space, let's consider one plane and say another plane. So let's call this plane 1 and plane 2. And just to match things, let's go ahead and call our first equation plane 1 and our second equation plane 2. So how do we show that two planes are parallel? Well, really what we're going to be using is just some fundamental concepts from geometry. So what do we know about these two planes to start with? Well, we know for each of these planes we have a vector that's perpendicular or normal to them, right? So we have, say, the normal vector, say for plane 1, we'll call it n1, with components equal to the coefficients of x, y, and z. So n1 has coefficients 1, -3, and 4. And likewise, we can find a normal vector, or a vector perpendicular to plane 2, again with coefficients 1, -3, and 4. So in our picture, again, what that means is n1, our normal vector here, is perpendicular to plane 1, and n2, our normal vector, perpendicular to plane 2. So where does the concept from geometry come from? Well, if we look at these two vectors, which are perpendicular to the respective planes, if these two vectors themselves were parallel, since they're perpendicular to the planes, that means the planes would have to be parallel. Now let's take a look at our normal vectors. Well, you can see they're exactly the same, which in particular, what does that mean? That we can say n1 is equal to n2, or moreover, we can write it as n1 is equal to 1 times n2. So they're scalar multiples of each other, meaning they're parallel, which confirms that the two planes are parallel. So to kind of state this as an answer, so since the normal vectors n1 and n2 are parallel, then the planes are parallel. Okay, so that shows us for part 1 that the planes are parallel. Now let's take a look at part 2. We want to find the distance between the two planes. So again, trying to get a visual of what we're going to do, let's take a look at our two planes in space. So we have plane 1 and say plane 2. So we want to find the distance between two planes. Well, what do we know how to do so far? What we know how to do is find the distance between, so the distance d, between some point off in space and a plane. So the distance there is found as, see, the absolute value of the dot product between the vector from p to q, dotted with the normal vector n, divided by the magnitude of n, right? Where again, q is the point that's off in space, p is the point on the plane we're finding the distance from, and n is a vector that's normal or perpendicular to the plane. So let's just suppose we're going to take plane 2 as our given plane, and we want to find the distance from that to some other point in space. Well, what we can do is take that point in space as a point on our other plane. So we'll take our point, say q, here, and we want to find some point p on our plane, given plane here. So PQ will be the vector between those, and then n will be the normal vector to our plane 2. So let's go ahead and fill this out. Starting with Q, how can we find a point on our first plane? Well, what we can do, looking at the equation of our plane, is we can find at least one point on there. If we say take two of the values of the variables to be equal to 0, we can solve for the remaining one. So if we take y equals 0 and z equals 0, that gives us x equal to 10. So we can find at least one point on that plane, let's call it Q, with x coordinate 10, y coordinate 0, and z coordinate 0. We can do the same thing for P on our second plane. So we can find the point P. If we look at the equation for our second plane, let y be 0, z be 0, we get x equal to 6. So the point P would have x coordinate 6, y 0, and z 0. And then the normal vector, right, our normal vector n, which is normal to our plane 2, which is actually our n2 vector from part 1, with components 1, -3, and 4. Okay, so what do we need to find? We have Q and P. We just need to find the vector from P to Q, and then plug everything in here. So let's go ahead and take a look at that. So our vector from P to Q, taking Q as our terminal point, P as our initial point, and doing component-wise subtraction. So we have 10 minus 6, which gives us 4, 0 minus 0, which is 0, and 0 minus 0, which is 0. And of course our normal vector here. All right, so now we can plug everything into our equation. So we're taking the absolute value of the dot product between the vector from P to Q and n. So the absolute value of the dot product, which is component-wise multiplication, so 4 times 1 is 4, plus 0 times -3 is 0, and 0 times 4 is 0. And then divided by the magnitude of n, and the magnitude is just the square root of the sum of squares of its components. So the square root of, say, 1 squared plus -3 squared plus 4 squared. Okay, and simplifying that, what does that give us? So up top, the absolute value of 4 is 4, and in the denominator, we have the square root of 1 plus 9 plus 16. So it gives us the square root of 26. So we're pretty much there, but we'll just go ahead and rationalize the denominator by multiplying top and bottom by the square root of 26. And that will give us 4 times the square root of 26 divided by 26. And simplify just a little bit more, noting that 2 goes into 4 2 times, and 2 goes into 26 13 times. So in the end, our distance can be written as 2 root 26 divided by 13. So there we have the distance between our two planes. Thank you very much.